Hello and welcome back to CS 11747 Neural Networks for NLP. I'm Graham Neubig and today we will be talking about attention. So we've talked previously about encoder-decoder models, which are very useful tools for conditional sequence generation, where we have one encoder and we have one decoder. And the models that we talked about previously basically took the encoder, calculated a particular vector from the encoded input and used that to condition the output of a language model or other variety of sequence generation model. And if we think about sentence representations, there could be a problem with this. So basically the problem is that we're asking the model to do a whole lot if we ask it to fit the entire content of a sentence into a single vector. And there's a famous quote by Ray Mooney: "You can't cram the meaning of a whole bleeping sentence into a single bleeping vector," to kind of colorfully describe this. And the basic idea behind attention is, what if instead we could use multiple vectors based on the length of the sentence? So instead of trying to go from a single sentence to a single vector, regardless of how long the sentence is, if we have 4 words in our sentence, we would like to essentially give the decoder model or the final prediction model access to each of the words in the sentence itself. And I like to give another analogy, which is I worked as a translator for a while, and if you asked me to read a whole text and memorize it and then try to translate it, that would be very, very difficult. But if you gave me access to the text and let me go back and reference the parts I was translating at any one time, this would be much easier. So basically, by keeping around vectors for each of the input words, this allows the model to go back and reference the ones that it thinks are most important at any particular time. So what is attention? The basic idea behind attention is that we encode each word in the sentence into a vector, and when decoding or making predictions, we perform a linear combination of these vectors weighted by something we call attention weights, and use this combination in, for example, picking the next word in a conditional generation task. So here's a concrete example. Let's say on the left side we have our decoder, which is trying to decode an English sentence. On the kind of top right here, we have an input sentence in Japanese. And we've gotten to the point where we're at the words "I hate," and we'd like to generate the next word. So from this, what we do is we use something called a query vector, which essentially indicates the current state of the prediction process that we're trying to do. In other words, the decoder state, and key vectors, all encoder states. And for each query key pair, we calculate a weight. So we run the first key vector in the query vector through some sort of function and calculate a weight of 2.1. For the next one, we calculate a weight of minus 0.1, et cetera, all the way through the sentence. And we then take all of these scores for the entire sentence, and we run it through a softmax to normalize them into values that look like they're on the probability simplex, like the alpha values here. And we can see that we've given a weight of about 0.76 to the first word, and this happens to be the word that we would like to be translating next. So after we have done this, we now have a relative importance weighting on the encoded words, and we take something we call value vectors. Usually this is also the encoder states, like the key vectors. And we multiply them together with the attention probability distribution here and do a weighted sum into a single vector. And now that we have a single vector of fixed size regardless of the input sentence length, we can use this in any part of the model we want. So to give a graphical example of what this can look like, This is an example of where we are trying to generate, I believe, a French sentence, and we're attending to the words in an English sentence. And when we do this, we can see that each time we generate a word, we essentially give some attention to the word that corresponds to it in the source sentence. And even when we kind of flip the order of words, like European Economic Area, the model is still able to focus on the appropriate words here. So one thing I should point out is this attention diagram that I showed here, while there is a pretty good alignment between, in this particular case, between the words that correspond to a particular word, it's not necessarily the case that the attention values will correspond to something that we think is an actual translation. So for example, here, when we have a period, we would expect that the period and period would be strongly aligned because they're obviously translations of each other, but that's not necessarily the case. Basically what attention does is it pulls in any information that would be useful in translating the next word. So attention can often be blurred, like the period example I've shown here. It's also the case that if you have a poorly trained or incompletely trained model, attention may be off by 1, or may even just attend to the final word in the sentence. So it's not necessarily the case that the attention values that you're looking at actually correspond to any alignment between the source and target sentences. So this is just something to be aware of, especially when you want to use attention for interpreting decisions or something like this. And in fact, there's even research that demonstrates that attention can be manipulated so that it focuses on things other than the things that you think should actually be important to solve the problem. So just a quick caveat here. So I talked about the basic idea of attention, and the idea is, we calculate a score function for each key query pair and then normalize them and do a linear combination according to this. But how do we calculate the scores for each of these? So if we assume that Q is the query vector and K is the key vector, there's a number of ways we could do this, starting with basically just run Q and K through a multi-layer neural network. So here we take Q and K, we multiply them by a weight matrix, take a nonlinearity, and then multiply it by a weight vector to get our attention score. So this is one option. This is flexible, and it can often be a strong option with very large data because, of course, the multi-layer perceptron is a universal function approximator and can approximate any function we would like to handle. So this is one option you may use. There's also bilinear functions, which basically take K and Q and multiply them by W in between, so that we kind of do a linear transform over the key vector before taking its dot product with the Q vector. Another option is a dot product attention. So what dot product attention does is basically just takes the dot product between the query and the key vector. This is simple and has no parameters, which is a good thing, but it also requires the sizes of the query and the key vector to be the same. So that's something to be aware of. And then there's also the scaled dot product function. So one problem is that the scale or the variance of the dot product increases as dimensions get larger. So if you have Q and K of a size 32, and then Q and K of a size 64 or 128, the 64 and 128's values are going to have a larger variance, and this will cause the attention to basically grow more peaky. and focus more on an individual word. So the fix is to scale by the size of the vector, scale the dot product by the square root of the vector. And this effectively controls your variance and makes sure that no matter what size of vectors you're using, you get approximately equal peakiness at the beginning of training. So we have some example code here that you can take a look at if you're interested in trying it yourself. It's quite simple, so you can go in and take a look and manipulate it if you'd like. And notably, if you want to play around with it, this code uses NLP attention, so you can implement a different variety of attention if you would like to do so. So I'm also going to talk about two very important varieties of attention. And the first one is self-attention. And so self-attention, up until now, what I was talking about is where we have query vectors that are basically from a decoder state and key vectors that are from the encoder states. And if we're talking about translation, for example, the query vectors would be in one language and the key vectors would be in another language and across different sentences. So this is often called cross attention because it's going across two different sentences and trying to attend to values in a different sentence. But self-attention, what it does instead is it tries to attend to words in the same sentence. And the way this works is basically if we want to calculate a vector for this here, it will attend to this is an example and do attention over all of the possible words and do a linear combination into vectors. So we do it over and over again like this. And eventually we get a number of vectors equivalent to the length of the sentence again. So one way to think about this is we had RNN-based or bidirectional RNN-based encoders that basically take in a sequence and calculate representations for each token in the sequence. And this is just another alternative way of doing that. So if you want to do a sequence level encoding, you could either use an RNN or you could use a transformer, or you could use any number of other models as well. But use an RNN, use attention, or use any number of other models as well. So the reason why you would want to do this, attention, for example, is if we want to pull in other information from other parts in the sentence to do things like word sense disambiguation. So if we have the word is here, how you translate this in a different language might depend on, for example, the gender of the noun that you're dealing with, or whether it is this is, or he is, or she is, or something like this. So basically what this would do is this would pull in information from the subject and the object in the sentence, which could then be used to do this sort of disambiguation. So yeah, basically this gives you a better idea of context in the sentence. Another important variety of attention is multi-headed attention. And the idea is basically that multiple attention heads focus on different parts of the sentence. To first give an intuitive example of a place where this could kind of be obviously helpful. If we have two heads, one head is deciding which is just a normal attention head that is pulling in contextual information from various pieces in the sentence. And another head is one that is basically deciding to copy words from the input directly into the output. And I'll talk about this a little bit later in the class today. And so if we wanted to do something like this, we might expect that the kind of head that's pulling in lots of contextual information would be kind of spread out more across the sentence to pull in all of the relevant context, whereas a head that was focusing on copying individual words would want to be more focused, like an alignment model, like I talked about before. And you can even take it a little bit further, which is basically that you just train independent heads completely randomly initialized, with the idea being that if you have different heads that focus on different parts of the sentence, they might essentially be able to pass in different varieties of information. So here's an example of attention to calculate the representation of the word making. And here the purple head is focusing on the word itself. The pink head is focusing on the previous word, which kind of makes sense because when you want to know more about a particular word, you'll probably want to know about essentially the immediate local context because it's very informative. And then over here, we also have other attention heads that are focusing basically on the object of the verb. So when you want to calculate the translation of like making, this is, depending on what you're making, you might be translating this differently. And because of this, knowing what is being made, knowing the object of this verb could be very useful. So we have some attention heads that are focusing on this object, some attention heads that are focusing on the word itself, and other attention heads that are focusing on the immediately useful context. And all of this is learned basically completely automatically. You just initialize them randomly and hope that they learn different things. You could even take this to the extreme and have one head for every hidden node, but this is a bit computationally expensive and not used very much in practice. So I've explained a couple varieties of attention, and I would like to do an interesting case study of what attention can do. The paper Attention is All You Need by Vaswani et al. This is a paper that hardly needs introduction if you've worked with NLP, but I think it's obviously worth covering in any NLP class. And this proposes a specific attention-based model architecture called the transformer. And specifically, it is introduced for the purpose of sequence-to-sequence modeling using an encoder-decoder framework. And notably, all of its kind of sequential encoding is based on attention. So the way it works is you first add something called a positional, or you first look up input tokens. You add something called positional encodings, where these positional encodings essentially are telling you which position the word occurs in. So position number 1 would get one position encoding, position number 2 would get another position encoding, et cetera, et cetera. And then after that, you run a whole bunch of blocks of self-attention and feed-forward networks, or multi-head self-attention and feed-forward networks. And this is done for the encoder part. So as I mentioned before, we can essentially swap in attention, self-attention for recurrent neural networks, et cetera, et cetera. And then on the decoder side, the decoder also uses attention, where it has self-attention and cross-attention. So it attends to the input, and then it has a feed-forward network here. The reason why this is so popular is essentially it gives strong results on translation in a wide variety of other tasks. And also it's very fast. And part of the reason why it's very fast is, unlike recurrent neural networks, which kind of have to incrementally process the input based on previous transformations, the self-attention here can be done entirely in parallel. So it can be done across an entire sentence all at once. So that's the basic overview. And one important thing is that it uses a bunch of tricks both in modeling the attention and in training. So it uses self-attention. So both the encoder-decoder use self-attention to encode each individual token as a linear combination of the other tokens in the sentence. It also uses multi-head attention, so it could use 8 attention heads, for example, all learned not really independently, I guess, but all learned initialized randomly and learned jointly together with the model. It uses normalized dot product attention, as I mentioned before, and it uses positional encodings. So basically, these positional encodings are necessary when you're using attention in this way, because otherwise you couldn't distinguish between two identical words that appear in different parts of the sentence. With respect to training, it uses a whole bunch of tricks. One trick is layer normalization, which helps ensure that layers remain in a reasonable range. And basically the way this works is it assures that the outputs have zero mean and unit variance after coming out of every individual kind of multi-head attention or feed-forward network here. So you'll notice just how much the model uses normalization. It uses normalization here and here and here and here and here. And this is important for getting the models to train properly. There's also a specialized training schedule. So it uses the Atom optimizer, but it adjusts the default learning rate to kind of warm up and then gradually cool down. And within the model, they also use something called label smoothing, which inserts some uncertainty in the training process and kind of helps avoid overfitting. And it also uses masking for efficient training. So specifically with regards to the final one, what is this masking operation? And so basically we'd like to perform training in as few operations as possible using big matrix multiplies. And we can do so by masking the results for the output. So when we're predicting the first word in the output, I, we would mask out I and everything following that. When we predict the second word in the output, we would hate. We would mask out hate and everything following that, et cetera, et cetera. So essentially, we have this gradual masking effect. But fortunately, if we create a masking matrix like this, this will allow us to essentially process all of these mask sequences at the same time, which can really improve the computational feasibility or computational efficiency of doing this training. So this paper was hugely influential and still is hugely influential. And the transformer model is essentially the new standard that we use in NLP for many, many different tasks. I would like to point out that it's not without failings, and it's a good idea to be aware that there are other alternatives, and there are things to be aware of when you're using these models. So transformers are very popular for good reason. They get good accuracy. They're fast to train. However, one issue with them is that they can be slow to decode at test time. And the reason why is basically it becomes harder to do this sort of masking efficiently at test time. And because of this, you need to spend more time decoding them, and the complexity can become quadratic. They also don't necessarily outperform RNNs, particularly on the decoder side of sequence-to-sequence tasks. So this paper by Chen et al. Demonstrates how RNN-based models actually do slightly better in kind of translation-style tasks. And also transformers can be hard to train on small data. They're relatively brittle. So my conclusion here is to definitely use them, but also be aware of the limitations and don't just kind of unquestionably say a transformer is the way to go without thinking of other alternatives. So now that I've covered the transformer, I would like to go into a bunch of other kind of alternative methods for doing attention, either from the modeling perspective, the training perspective, or what we attend to. And these are all things just to keep in the back of your mind in case you would like to pursue research direction in the area of something that improves on attentional models. And so the first one essentially is how do we create better models of attention? And specifically, this paper by Cohn et al. Actually has lots of different methods it's proposing, and this is one of them. The idea is that attention from the last time step tends to be correlated with attention this time, as we can see here. So basically, we gradually step through the sequence, and we're stepping through forward one by one, and then backward one by one, and then forward one by one. So the idea is we wouldn't want, huge jumps in attention every time step. So what this does is basically it adds information about the last attention value when making the next decision. Another alternative variety of attention model uses hard attention. And basically the idea is instead of a soft interpolation between the outputs, we're making a 0-1 decision about where to attend. So there's reasons why you might want to do this or might not want to do this. One reason why you might not want to do this is it can be harder to train because, as we've talked about before in this class, any 0-1 decision that's using like a step function or something like this will have trouble with gradient propagation and requires something like reinforcement learning or other tricks. However, there is an argument that this can help interpretability of models. And what this paper shows is basically if you have a hard attention value, you can kind of highlight individual parts of, for example, a text that you want to classify and use those highlighted parts to justify decisions about that text. Another variety of attention to be familiar with is monotonic attention. And in some cases, we might know the output will be the same order as the input. This could include speech recognition, where generally the output phonemes are in the same order as the input speech frames. Incremental translation, where we want to translate a few segments at a time within a sentence. Other things like morphological inflection, also summarization might be largely monotonic. And so there are methods, like the one cited here from Yu et al. 2016, that essentially enforce this monotonicity and maybe even hardness constraints as well. So this would be a good thing to know if you're working on essentially these sorts of problems. There's also some better training methods for attention. One really important one, which actually can be used at training time or test time, is coverage. And the problem is that neural models, especially when they're not trained well or when they're tackling a very hard task, they tend to drop or repeat content. And one solution to this is to model how many times words have been covered. So one way you can do this at training time is imposing a penalty if attention is not approximately 1 over each word. And another way you can do this is on the modeling side, adding embeddings that indicate how much particular words have been covered. There's also heuristic methods that basically downweight at test time the probability of words that had been covered many times before. And this was used in things like the original Google machine translation models. So lots of methods to incorporate coverage here. Another method that I have used in the past and can be useful is this bidirectional training. And the intuition is that if you have a forward translation model and a backward translation model, or forward sequence model and backward sequence model, the attention diagrams between them should be approximately similar. So, if you're translating a content word forward or translating it backward, it should still be aligned to its counterpart in the other language. So this method here essentially trains so that we get a bonus based on the trace of the matrix product in both for training in both directions. And essentially, the more these two overlap, the higher this trace value will be. Another method, which is useful maybe from a accuracy perspective, but also quite useful from an interpretability perspective, is supervised training. So sometimes we can get gold standard alignments a priori, like we have humans annotate which words they think are important for translating other words, or maybe we could do this heuristically by finding identical words in the source and target and making sure that they get aligned to each other. Or alternatively, we could also have a strong alignment model that is pre-trained. And then we can go and train the model to match these strong alignments by adding supervision. Okay, and now I'd like to go to the last part. So I've talked about self-attention, I've talked about attention in a translation model. But what else can we attend to, or what else can we use attention to assist us in training our models? So one thing that we can do, which is useful and fairly widely used, is copying words from the input sentence or sequence. And we're still doing attention to the input sentence or sequence, but we can directly use a copy mechanism that essentially allows us to predict, for this particular word, I would like to copy this directly into the output. And this is good for a number of reasons. Number one, if you're going to have an output that very often contains words in the input, it's much easier to copy them from the input directly than it is to kind of like hope your embeddings get in the right part of the space and generate the word you want to generate, as opposed to some other semantically similar word. And so the way this basically works is you have a interpolated probability distribution where you have the probability of generating the word that you want to copy, either from the underlying vocabulary or from copying from the input. And then we have a softmax over the input words, and the word that gets the highest softmax probability over the input is the one that would end up being copied. Another thing that we can do is we can use the input sentence to influence the probabilities of the output. So if you have a translation dictionary, for example, or other variety of dictionary that maps between the input and output, you can use it to bias the outputs. So essentially what we do here is we do attention, and then we have a whole bunch of different words that we might have in our output. And we also have a dictionary probability matrix, which basically says that this input word could be translated into this output word. This input word could be translated into this output word, et cetera, and maybe we get this from word alignments or from a manually curated dictionary, et cetera. And then based on this, we do an interpolation according to the attention values to get a dictionary probability for the current word. And here, if we have a lot of attention on Tunisia, and our dictionary says very strongly that this should be translated into Chunijia in Japanese, for example, then this will give us a very high dictionary probability, which in turn will allow us to kind of upweight the probability on the output side. And this can be useful for generating rare words if we have an accurate dictionary over the translations of rare words. Another thing we can attend to is previously generated things. So, for example, in language modeling, if we have already generated particular outputs, we can attend to the previous outputs that we've generated, and we can even, copy them into the next word. So this can be done either for language modeling, or it can be done within translation. So the transformer decoder is essentially also attending to previously generated things in the output. We can also attend to various modalities. So attention actually originally came about for attending to particular parts of an image. And it's also been widely used in speech, and there are attentional models for speech as well. And I've cited a few old papers here, but they've also been using transformers and newer varieties of self-attention, et cetera, more recently as well. There's also hierarchical models of attention. So the basic idea here being that we first want to attend, for example, to individual words in a sentence. And then after we've attended to individual words in the sentence, we aggregate them into kind of a vector for a single sentence. And then we attend to the vectors in the sentence vectors in an entire document, for example. So we can see the word encoder and word attention here, and then the sentence encoder, sentence attention here. So these are very useful if you are handling longer documents. But one caveat is that there might also be other kind of non-hierarchical models that we can use as well. And we'll be talking about these in a later class when we talk about document processing. And finally, we can attend over multiple sources. So for example, if we have a translation method where we want to, where we have a target in English, and then we have two input translations, German and French, we can attend to both of these at the same time. And there's a comparison of multiple strategies here in this paper where they discuss hierarchical methods, flat methods, et cetera, et cetera. And then finally, we can also attend to, for example, a sentence in an image to do multimodal translations. So we can, attend to multiple things of different varieties as well. Okay, so that is all I have for today. So hopefully this was useful, and for people in the class, I'm looking forward to discussing at the discussion session. Thanks.